NASA has selected a study that asks whether humanity could place a controlled cloud of microscopic particles between Earth and the Sun, cutting incoming sunlight by about 1.16%. The headline is dramatic, but the first buried signal is crucial. NASA is not preparing to launch this system. It funded a Phase 1 feasibility study under its Innovative Advanced Concepts program. NIAC exists to test ideas that sound like science fiction. Its job is to find out whether the physics, engineering, and mission architecture deserve deeper work, not to approve deployment. The proposal is called DimSun. Its author, a researcher at NASA's Jet Propulsion Laboratory, describes a controlled dust cloud positioned near the Sun-Earth L1 point. L1 is a gravitational balancing region roughly along the line between Earth and the Sun. Spacecraft there can remain positioned with comparatively modest corrections while continuously observing the sunward side of Earth. DimSun would use particles just 0.3 of a micrometer in radius. The proposal describes them as 90% hollow, a design intended to scatter sunlight efficiently while reducing the mass that must be transported. The cloud would not be a solid screen. It would be an enormous, diffuse population of particles, thin enough to remain almost invisible yet collectively able to reduce the amount of solar energy reaching Earth. Earlier studies imagined releasing dust near L1 and replacing it as the cloud drifted away. DimSun's central innovation is active control of multiple spacecraft would use repulsive forces to resist that orbital decay. According to the proposal, that control could remove the need to replenish the cloud every 100 days. The spacecraft would continually shepherd particles that would otherwise disperse. The proposal also calls the system reversible. Switch off the control spacecraft, it says, and the particles should drift apart within roughly 100 days, allowing sunlight to return to its previous level. That sounds reassuring, but engineering reversibility is not the same as reversing every consequence. Climate systems, ecosystems, agriculture, and politics may continue reacting after the hardware is switched off. Solar radiation modification addresses temperature by changing incoming energy. It does not remove carbon dioxide already in the atmosphere, and it does not directly solve ocean acidification. Its appeal is speed. Greenhouse gas reductions work by changing the long-term balance. A solar intervention could, in principle, influence temperature much faster, buying time during extreme warming. But speed is also the danger. A system capable of changing planetary temperature quickly would create pressure to act during heat emergencies before every regional effect was understood. The DimSun page gives a rough one-time cost estimate of $134 billion. That number belongs to the proposal. It is not an approved NASA budget or an independently verified program cost. The author argues that this would be far cheaper than giant space-based occulting structures and cheaper over the century than repeated stratospheric aerosol injection. Those comparisons are claims to be tested, not settled procurement facts. Even if the physics worked, manufacturing trillions of precise hollow particles would be a major industrial challenge. So would launching, distributing, and monitoring them without creating new hazards in space. The control spacecraft would need extraordinary reliability. A cloud designed to affect the whole planet could not depend on fragile maintenance, uncertain communications, or a single operator's uninterrupted funding. Then comes measurement. Operators would need to know whether changes in sunlight were producing the intended global average without hiding harmful regional shifts in rainfall, monsoons, or seasonal patterns. NOAA warns that solar radiation modification could benefit some places while harming others. A cooler global average does not guarantee better conditions for every country, ecosystem, or farming region. That creates a question science alone cannot answer: who decides the acceptable trade-off? The country operating the system, a coalition, the United Nations, or every state that might be affected? There is currently no universally accepted governance framework for deploying solar radiation modification. Research exists, modeling exists, but there is no settled planetary rulebook for consent, liability, or control. Liability becomes especially difficult. If one region experienced crop failure or disrupted rainfall after deployment, proving exactly what caused the harm could be scientifically and legally contested for years. Control also creates power. The organization capable of adjusting Earth's incoming sunlight would hold leverage unlike any existing energy company, central bank, or technology platform. Even a cooperative system would face security risks. Sabotage, cyber intrusion, disputed commands, or simple technical failure could become international crises because the effect would cross every border. There is also termination risk. If the world relied on artificial cooling while greenhouse gases continued accumulating, a sudden stop could expose the underlying warming much faster than societies were prepared to handle. Supporters of research argue that refusing to study the option does not make the climate risk disappear. Better modeling could reveal fatal flaws before desperation pushes governments toward poorly understood action. Critics worry that technical progress can create political momentum. Once money, institutions, and careers form around a capability, the boundary between studying it and normalizing it may gradually weaken. Another concern is distraction. A seemingly cheaper temperature control could weaken pressure to cut emissions, even though it would leave carbon pollution and many associated harms in place. DimSun's value may therefore be less about presenting a ready answer and more about exposing the real questions early: materials, orbital control, climate attribution, international law, and democratic consent. The study's claimed reversibility is still important. A system designed to disperse after shutdown is fundamentally different from a permanent structure. But that feature must be tested under failure, conflict, and imperfect control. The same is true of cost. A rough estimate can make an idea look affordable next to global climate damage, but first-of-a-kind space systems regularly reveal expenses that early concepts cannot fully capture. NASA's selection does not mean the agency endorses solar geoengineering. It means one proposal was judged worth investigating among a portfolio of deliberately unconventional ideas. Still, the fact that this idea is being studied matters. Climate intervention is moving from abstract debate into specific engineering proposals with particle sizes, orbital locations, control architectures, and price tags. The hardest component may never be the dust cloud. It may be building a system of consent strong enough for billions of people to live with a decision that changes the sky above all of them. DimSun is not a plan to switch off the sun. It is an early warning that planetary-scale tools may arrive before planetary-scale rules. The signal is not just in what we can build, but in who gets to decide.